Howdy, everyone, and welcome to the next lecture in statistics. This should be a relatively short lecture compared to some of the ones we've had in the past because today we're introducing something brand new. We're finally getting into hypothesis testing. It's been a while coming, but we're ready to go. So, the big thing here is this idea that we actually want to develop a test. We actually want to develop some way to decide what's going on. So without further ado, let's just see what we're even trying to do here. So one of the first things that we might consider is we might just consider a scenario. So let's suppose a school superintendent discovers that the mean SAT score is 1050 and his school averaged 1100. Can he conclude his students as a whole are above average? Can he conclude that his school is just the bestest school ever? Um, and the thing here is that as we've seen with confidence intervals, which are very, very tightly tied to what we're doing here, we're going to see that confidence, as we go on through this, we'll see that confidence intervals are extremely close to hypothesis testing. Confidence intervals give us some insight into what's going on here. So can he conclude his students as a whole are above average? Well, there is nowhere near enough information in this statement. There is nothing like enough here. We need to know what's the standard deviation. If the standard deviation is only, let's say, 60 points, then maybe. If the standard deviation is 300, maybe not. How many students does he have? The more students he has, the more the central limit theorem is going to reduce that standard deviation. The more we're going to see the standard error of the mean be brought down, your standard deviation over root n. So here, if the standard deviation is maybe 200 and he's got, let's go with 36 students, well, then the standard error of the mean ends up being about what, 33? 30, just 200 over 6, 100 over, yeah, 33 and a third. Um, and here, that means that you're looking at something where you're going to have a z-score of about 1.5, which might not, which is pretty far, but not ridiculous. So, can he conclude that students as a whole above average? Probably, if those were the numbers, probably not, but we'll get into that later. So, in fact, we're going to see kind of what's going on here. So, our methods. Um, if we're looking at comparing kind of specific chosen samples to a population, this is going to be our most common test. We might compare two samples together. This is also an exceedingly common test. As we learn more and more types of tests, we'll find more and more ways to use these hypothesis testing methods to interpret more and more types of data. For the purposes of this class, we're really only looking at means, we'll be looking at proportions, and later on we'll be looking at expected categorizations, expected distributions, in something known as a Pearson chi-squared test. So for now, though, what we're really doing is we're generally following these steps. We'll first define the population that's under study. For the most part, for the purposes of practice problems and things like that, this will be done for you. For the purposes of your own experiment, which will happen before the end of this year, this will be part of it. You'll need to figure out, who am I testing? What am I working with? Next up, you need to state a hypothesis to be investigated. This is going to be today's class. You'll decide on a significance level. This is going to be tomorrow's class. This is going to be the next class. And then once you've done these things, this is all before you've even gone out and collected data. You'll have done all these things before really fully completing the experiment to begin with, or fully completing your analysis of any of your data. And one of the reasons for this is if you're deciding on a significance level after you have your data, this kind of leans heavily into something that is the less reputable parts of statistics. You'll see people decide on a significance level so that they can get something significant. This is one of the most blatant types of what's known as p-hacking. And we'll talk more about that as we talk about kind of how to go about creating a rigorous but reputable experiment. Or rigorous and reputable experiment, rather. So let's take a look at the last few steps here. Step 4 is just to go ahead and actually select the sample, collect the data. Step 5, this is where we're doing the math now. We're actually performing the calculations. This is, despite the fact that this is going to be mainly what we're doing in this class, this is one of the shortest and least involved steps in here, because for the most part, selecting the sample and collecting data is a pretty big deal. Surprisingly, deciding on a significance level can result in some pretty strong arguments. Performing the necessary and relevant calculations, that's just numbers. Sometimes you need to be clever, sometimes you need to discuss what you do and don't keep. If there are outliers, or do you throw them out, do you keep them? That certainly is involved in this step. But it's surprisingly, despite the fact that that's really what we're focusing on, I would say it's the step that's prone to the least argument. And then finally, 6, and this should be underestimated in its importance, is to draw a conclusion. And that's an appropriate conclusion, which we will certainly talk about in future classes. There's 2 methods for this, which will be a traditional or confidence interval method. This is the one we're going to kind of look at. This is the one we're going to kind of look at as a way just to compare what's going on. And then we have the p-value method. The p-value method is the professional standard. This is the one that realistically I want us using at the end of the year. So let's talk a little bit about some vocab here. This is what we're going to be dealing with today. So let's talk about hypotheses. So a statistical hypothesis is a conjecture. It's a conjecture about a parameter. And remember, a population parameter is our baseline. A population parameter would be like a thing like a mean, a thing like a standard deviation, a thing like a proportion. It's information about the population. So this hypothesis is a conjecture about what that parameter might be. And this hypothesis, it might be true, it might not be true. We don't necessarily know, or more than we don't know, we necessarily don't know. If we knew, we wouldn't really need to do an experiment. It might or might not be true, and for the purposes of designing our experiment, it really doesn't matter whether or not it's true. Our experiments are going to be built around the assumption of what things would look like if it is true, but that doesn't mean it has to be. So, the null hypothesis, which is written H sub 0, often pronounced H naught. This suggests that there's no noticeable difference between whatever we've tested and whatever our conjectured value for our population parameter was. So if we're assuming a mean of, let's say, 7, or let's go back actually and use the one up here. If we're assuming a mean of 1050, the null hypothesis would be that there is no notable difference between our sample, how our school did, how this superintendent's school did, that 1100 and the 1050 that is actually the population parameter, there's no notable difference between the two. And this is our baseline. We always assume that our data point comes in an appropriate way from the population in question. So our baseline is always the null hypothesis, that there's no difference between our tested parameter, between our sample, and the actual specific value that we get. And or yeah, and the alternative hypothesis then is the opposite of the null, written H sub 1, or you'll see people say H alt. I certainly don't. H1 is fine. But anyway, you also see HA. That's the other one you'll see. But written H1, this suggests the existence of a notable difference between our test value and our assumed parameter, our assumed population value. And what that means is that whatever's going on, whatever way we wanted to see if there was a difference, there ended up being evidence that there was one. And we're going to be very deliberate with our language as we move on. If we ever end up finding that there is some sort of significant difference where I'm going to use the word embrace the alternative hypothesis instead of the null, it's always that evidence suggests a difference. It's never that there is one, right? Because we don't know. The whole point of what we're doing here is this statistical hypothesis may or may not be true, right? So if we aren't sure one way or another, it's only what evidence suggests. It's never an absolute. All right, so we'll discuss that a lot. Trust me, you'll get tired of hearing it. So the idea here is that we really are just trying to use data to make a decision about whether or not we are going to reject our null hypothesis. We always begin by assuming the null is true. And we're going to use collected data to decide whether or not to reject that initial assumption. So, here's kind of an important note that I've already talked a little bit about, is this idea of a notable difference. We're going to be looking to test things in very specific ways. And the coming slides are going to show that. And that's the purpose of today's class. So if I really want to see if a population parameter, or if a certain parameter has increased since a previous measurement, or if I want to see if my school scores higher on the SAT, and I don't care if it's lower, then I really only would call a notable difference one where there's an increase. It staying the same or even decreasing is not notable to me. For the record, something like saying, oh yeah, I only care about an increase in the SAT scores, so no other change means anything to me, sounds really skeevy. And violates my personal rules for whether or not to use kind of a one-directional test. But we'll talk about that. Anyway, let's take a look at some examples of what we mean by how, or of what we might set up in terms of how we test things. So here's an example. A medical trial is underway, and prior to medication, patients have an average heart rate of 80 beats per minute. We want to test if whatever medication we're working with changes heart rate. So here, our null hypothesis is that there's no change. So there is no notable difference. In other words, the mean is 80. The mean for the data we collected is 80. And it doesn't have to be exactly 80. It just needs to be close enough to 80 that we have no reason to think that this is erroneous. The alternative hypothesis is that there is a change. So we say that H1 is that the mean is not equal to 80. And this is it. This is all we're doing here. So our null hypothesis is that the mean is 80. Our alternative is that the mean is not 80. And that's it. Here we just care if there's a change in either direction, right? I only say I want to test if the medication changes heart rate. So if there's a change in either direction, could be an increase, could be a decrease. Both of them matter to me in terms of determining whether or not something significant happened. This is known as a two-tailed test because there's two directions it could go. It could go up or down. Let's look at a second example. New filaments are being tested to increase the life of light bulbs. The mean lifetime of prior filaments is 100 hours. What are the null and alternate hypotheses? So here, we only care about an increase. This is an example of something I think would be dubious for only caring about an increase, but that's the way I've written this problem to give an example of what's going to be a right-tailed test. So we're going to run with it. For the record, I think this is dubious because it would, as a light bulb manufacturer, if my new filament decreased were to do what I didn't expect and were to decrease the life of light bulbs, I would want to know. I would consider that something important to know. So this idea of only caring about an increase is at best naive and at worst actively misinformative. Actively providing misinformation, rather. Let's use correct grammar. So dubious setup, but we're running with it just to give an example of what a right-tailed test looks like. So here, we only care about an increase. So the null hypothesis is that there isn't one, that no notable change happens. So there is no increase. Notice that the null covers, there could be a decrease. The mean could be less than or equal to 100. That's not what we're testing. So that falls into the null. That falls into no notable change. No change that I care about happened. You will see some people just write equals 100 here. Both notations are considered proper. I personally prefer this one, but you're welcome to just say equals 100 and I won't mark it wrong. The alternate hypothesis is the one we care about. This is the direction we're looking for, right? We wanted to see if the life of light bulbs increased, so we want to see if our new mean is noticeably above 100. And this would represent a rejection of this idea that it's, that the mean is not noticeably above 100. So here, our alternate hypothesis is the thing that's kind of changing in the direction that we want to see a change. And so it's written, H1 is, or H1 colon, mean greater than 100. So here we only care about an increase. This is known as a right-tailed test, with the idea being that if we have a bell curve, let's just draw one quickly. If we have a bell curve, a right-tailed test would say I only care about a significant increase, so I only care about something over here. Notice how this is kind of on the right tail of the bell curve. And we'll talk more about this in coming slides, but I might only care about something where it's like, wow, that was incredibly far away. Like if in this example, my 100 is here, then if I'm going this way, if I'm way off over here, that's noticeably higher than 100. So that might be something I'm looking at. That's why I call it a right-tailed test, because the part I care about is on the right. We'll see more about that in the next discussion. So back to what we were talking about earlier. Let's move on to the last one, a left-tailed test. Billy Joe Jimbob is testing to see if his new installation has helped lower heating bills during the winter by comparing the average of his new bills to the average of his old bills given similar conditions. The old bills averaged $78. Once again, probably something that would be dubious to use a one-tailed test for. You're going to see me talk about that a lot. in my opinion, and this is purely my opinion, um, different statisticians, different people who have worked with different types of data will have different feelings about this. But for the most part, I find one-tailed tests to be dubious. I for the most part think that there are very few circumstances where you only ever care about a change in one direction, where you'd actually be interested in the results of the test in the first place. But anyway, Billy Joe Jim Bob is testing to see if his new installation has helped to lower heating bills. So we want to see if something's lower than his old 78. So the null hypothesis is that there's no decrease. The null hypothesis is that things are unchanged in any way that we care about, at least. So the mean is not lower than 78. In other words, greater than or equal to 78. So if somehow the heating bills went up, I wouldn't, this, for the purposes of this test, at least, I wouldn't detect that. And that's kind of one of the shortcomings of a one-tailed test, of like a left-tailed test. But what happens here is we say, okay, great, the null is that the mean is still 78 or even higher than 78. The alternate hypothesis is that the bill has indeed decreased. So the new mean is below $78. Neat. So again, the thing that we're trying to test represents our alternate hypothesis. We were testing here if there was a change, so the alternate hypothesis was the one that was a change. It's no longer equal to 80. We were testing here if there was an increase, so the alternate hypothesis represented an increase. We were testing here if there was a decrease, the alternate hypothesis represented a decrease. And again, in the same way that the previous test was a right-tailed test, we're looking for a decrease, so this is a left-tailed test. So here, this is just a nice chart that shows exactly what we talked about, and here you can even see, side note, in almost all cases, it's perfectly correct notation to write the null hypothesis. It's just the mean is equal to whatever starting value we have. This is you'll see plenty of people use this notation, and no one bats an eye. No one balks at it. The tail that we care about is associated with the alternative hypothesis, or the alternate hypothesis, not the main, or not the null. What we're going to do, what I'm going to just briefly take a look at here is just drawing a conclusion, and then also talking a little bit about what a one-tail versus a two-tailed test represents, what a right tail versus a left tail versus a two-tailed test is. Because here, the thing that's going on is mostly we're just seeing, like, yes, these are hypotheses, and you're not really getting a lot of idea of why they are what they are. So the conclusions. The idea here is that we're deciding whether or not to reject the null hypothesis based on the evidence that we've gathered, and specifically how that evidence suggests that what difference there is between our sample value and our k, our baseline, and whether that suggests that something significantly different is going on. So so what might happen here is we might say, like, okay, I'm looking for some significant difference between my sample mean and k, and whatever kind of value that I'm working with. So here I've chosen k, right? And I find that there's a difference, and so now I need to decide, is that difference significant enough? And so that's the key point in how we design hypothesis tests, is how big a difference is big enough for us to decide that the null hypothesis is no good, that the null hypothesis does not seem to fit with what we're seeing. And so what we'll do is we'll say, oh, well, maybe I just say that I need to be far enough away from what I expect, and here I would expect the mean. I would expect to be in the center. I need to be maybe far enough away that I decide, oh, well, this is unlikely to happen by chance. And if I'm this far away from the mean, if I've gotten a result that's out here, then maybe I say, well, it's I I'm going to reject the idea that this happened by chance. It's more compelling to me that this happened because something different is going on. So here, the critical region that I'm pointing out is the region in which I say, hey, if I get a z-score for my test value, not my population value, because the population value is going to be the mean. But if I get a z-score for my test value that's out here, this is when I'm going to say, well, the null hypothesis isn't good. That the null hypothesis isn't working for me, so I'm going to reject it. And that means if I'm rejecting the null hypothesis, that is evidence suggesting that something else is going on. And what that leaves me with is this idea that that what I'm left with is the alternative hypothesis. What I'm left with is is this significant evidence that that something different is happening. And there is a fine point between saying rejecting the null and accepting the alternative, because you're not accepting anything. Again, we make no assumptions about the truth or falsity of our hypotheses. Going all the way back here, the statistical hypotheses that we're working with, they might be true, they might not be true. We're not accepting a dang thing, but what we're doing is just saying that we don't like the odds that the null hypothesis remains true. We that doesn't jive with what we're seeing. That's all we're saying. So here, out here is where we're saying, hey, this is a pretty significant difference, and this is a right-tailed test because the value that we're looking for is on the right. Here's a left-tailed test. The value we're looking for is on the left. Whatever z-score we found is noticeably lower than the mean. And then for a two-tailed test, it's just noticeably different. So maybe it's really low, or maybe it's really high. So if we go back to the two-tailed test up here, an average heart rate of 80 beats per minute, maybe we find that I'm ending up getting a average heart rate of 85 beats per minute after medication, and that represents a very significant increase. So that represents maybe like a z-score of positive 2.5, let's say. So that might be like up here. And then we say, oh, hey, look, that's pretty significantly different, so I'm going to reject the null, and that's what we're going to do. And that's how we're going to set up these experiments and draw our conclusions. So this is the idea. So the last thing I want to leave you with in terms of one-tailed tests versus two-tailed tests is these two examples here have exactly the same level of test accuracy, have exactly the same level of confidence in the result. And yet you might notice that this particular cutoff is a lot closer to center for the one-tailed test than it is for the two. And so what happens here is a one-tailed test has much more power to detect a significant difference. It's going to call something significant much earlier, but only on the side that we care about. So if something weird is happening over here, we're not going to notice. But if something weird is happening over here, we're going to notice sooner. It's easier for us to tell a difference with a one-tailed test than with a two. And that can be nice if you're looking for just trying to see if something, if you're trying to get a general idea of maybe if something special is happening or if something strange is happening. If you're trying to convince somebody that you found this noticeable difference. Once again, the fact that it's easier to find a notable difference with a one-tailed test actually probably works against you for the purposes of making a compelling argument. Because someone's going to look at you and go like, well, yeah, but you just chose that because it's easier, and you're effectively getting accused of building your test around of building your test around the result you want rather than building your result around the test you made. And that's where you don't want to be. You really never ever want to be in a position where you where you really never want to be in a position yourself or be dealing with other people where they're drawing a conclusion based on the conclusion they want to draw, where they're forcing a conclusion they want. And of course this happens, and it's disheartening anytime it happens. But that's if you read a book on lying with statistics, this is what they're going to talk about, is how to make it something seem significant. We'll talk a lot more about that in the next lecture. We'll talk a lot more about that in the near future. For now, I just want to leave you with this idea of determining how to set up hypotheses, because if you're setting these up incorrectly, it's going to be really tough to draw the right conclusions. So here, the idea here is, if you're looking for a difference just in any direction, that is what's known as a two-tailed test, and your hypothesis is that there is no change for the null, that the null is the mean is equal to whatever our baseline was, and the alternate is that the mean is different from whatever the baseline was. It's just not different, different. If we're looking for an increase, this is known as a right-tailed test. So here, the alternate hypothesis is that there is an increase. That the sample mean is noticeably higher, or the mean that represents our sample data is noticeably higher than whatever baseline we're working with. The null hypothesis is that there is no increase, that there's no noticeable increase. And finally, if we're dealing with a decrease, if we're testing to see if there's a decrease, then the alternative hypothesis is that there is a noticeable decrease, that the mean is noticeably lower than whatever baseline we had, and the null hypothesis is that the mean is not lower than whatever baseline we had. So the mean is equal to or greater than that baseline. So here, this is what's to keep in mind whenever you're picking your hypotheses for a test. Whatever you are looking to see, like if it happens, that's your alternate hypothesis. And then the null is just that change not happening. Whatever change you're looking for, that specific change not happening is your null. And that's kind of what we're dealing with for picking hypotheses. And that'll do it for what you need to know for now. More on hypothesis testing in the next video. So until next time.